Related rates. We're going to take a look at an example with related rates as we look at a rocket being launched from a launch pad with being tracked by a radar station 3 miles away. We're wondering what the vertical speed is when the distance from the radar station is 5 miles and the distance is increasing at 5,000 miles an hour. Now if you take a look down here, here's your launch pad. Here's your radar station, 3 miles away always. Now, your rocket is going up, and as it goes up, you'll notice the height changes and the distance from the radar station changes. Here you're dealing with speeds, which are rates. In the context of our problem, the height of the rocket and the distance from the radar station change. So, we know at one point our distance from the radar station, z, will be 5 miles. But it's not always 5, so we got to still leave it as a variable. We know this rate, which is speed, which is distance over time, which would be the derivative of your distance with respect to time, is increasing at 5,000 miles an hour. Whenever you see a rate in a problem, remember that means your derivative. When you look at your units here, it's units of distance over units of time. So here we have our units of z and z's distance over the units of our time. We also want to know what is the vertical speed. Well, that's a rate again. We're looking for our dy dt. So we want to write down what it is we have, what we're looking for. Now we want to find an equation that relates our variables. And that would be this here. Because our variables are z and y. Here's our equation that relates z and y. But we have the derivatives with respect to t. So we need to go ahead and take our derivative with respect to t. Well, the derivative of the 3 squared, that's a constant. Take your derivative of your 2y, or y squared. You put the 2 in front, decrease your exponent by 1. But then remember, you got to do the chain rule. Multiply it by the derivative of y with respect to t equals. Then on the right side, we'll put the 2 in front, decrease your exponent by 1, multiply it by the derivative of the inside of derivative of z with respect to t. This does simplify a little bit. The 2's drop. Now, you have two options. Either go ahead and solve it for what you're looking for, dy dt, and then plug stuff in, or you can plug stuff in and then solve it. Here we're going to actually go ahead and plug stuff in and then get stuff or solve it. We know up here that z is 5, so we plug it in. We know our dz dt is 5,000, so we plug it in, and y is 4. And you might be wondering, why is y 4? Well, we know it's always 3 over, so it's 3 squared plus y squared equals 5 squared. When you go ahead and solve that, you then end up getting y squared to be 16, so you really get plus or minus 4. But in the context of our problem, we can't have a negative, so it has to be the positive 4. So now we go ahead and get dy dt by itself by dividing by 4, and we get 6,250 miles an hour is our rate. It's increasing because it's positive. These are the steps you're going to want to follow whenever you're solving a related rates problem. These are the steps that we followed on the last problem, and so we're going to do these on pretty much all the next problems. Here we have a rectangle. Our rectangle has its length decreasing and its width increasing. So you can see as I do that, that the area changes. And well, what we're wondering is, What's the rate of change of the area? Your rate of change of the area is a dA dt, and that's what it is we're looking for. You also have that the length is decreasing at this rate. Here our length is x, so our length is decreasing. That at that rate it would be a dx dt, it'd be negative 5 centimeters per second. We also have up here our width is increasing at 3 centimeters per second, so that's our y, and so that's the dy dt. Your variable that relates x and y to your a is just your area equation. We also know that our x is going to be 100 and our width, or our y, will be 50 when we're trying to evaluate this problem. But for right now, we don't want to plug in those numbers because these are variables, they're changing side lengths. After we've taken our derivative, then you can actually go ahead and plug those in. Take your derivative of both sides with respect to t, the derivative of a with respect to t, equals, and then on the right side it's really a product. You're multiplying things together. So the derivative of x with respect to t times the second plus the first times the derivative of the second. Well, we're trying to find dA dt, so we could just go ahead and plug in everything that we have. Our dx dt is negative 5, y is 50, x is 100, dy dt is 3. We get negative 250 plus 300, so we end up getting 50 centimeters squared per second. We know it's 50 centimeters squared because our units have to match the derivative. Here it's units of the area, so it's going to be units of the area because it's an area on top with respect to time, so the time has to be on the bottom.